So it's a great pleasure to have Professor Kazushi Ueda from the University of Tokyo as our second speaker for the morning session. And he's going to talk to us about non-commutative local Calabi-Yau threefolds. So please go ahead, Professor.
Thank you very much for introduction and for the opportunity to give a talk in this nice conference. So, I have put this slide on Google Drive and also put the address on the chat. So you're welcome to download it. And if somebody who came later couldn't read the chat, then please let me know and I will copy it again. Or maybe I can put it on the website or anyway. So and I'll discuss to begin with, let me recall something that probably many of the audience already knows. So the local P2, which is a prototypical local toric Calabi-Yau threefolds. So there's a quiver describing local P2, which is this one on the screen. And so it's a quiver and it is equipped with potential consisting of these 6 terms. And so I will go on to the next page. So I do suggest to download the slides so that you don't need. I don't think it's possible to memorize all the slides. And if I'm giving this talk in person, then I will draw these things on the blackboard. And usually, at least in the math conference, and I think in most of string theory conference, there's a blackboard is big enough to keep many figures and formulas and so on. But on the computer screen, I think it's not very easy to keep all the figures and formulas. So I go on to the next page. But I don't assume you have photographic memories. I assume that you have the slides and downloaded in your computer. And anyway, so the local P2 is toric, and so the quiver that I have shown in the previous slide is described by a diamond model. I think diamond model is one of the theme of this conference, and so maybe I can draw that diamond model here. One advantage of using computers instead of blackboards is we don't have to worry whether we should call this white node or black node. I think everyone is agreed to call this white. Anyway, so there are 2 nodes, black and white, and so there are 9 edges, and so these are dual to arrows of the quivers, and face of the diamond model is dual to or correspond to the vertices of the quiver, and then these nodes are correspond to monomials in the potential, and so 6 monomials in the potential on the previous slide correspond to these nodes on this diamond model. And so this diamond model essentially gives everything you have to know about local P2. And so this quiver describes the derived category of coherent sheaves on local P2. So this is a very nice combinatorial way to encode the geometry of local P2. And moreover, this very nice story extends to all toric Calabi-Yau threefolds. So that's what diamond models are about. And so there are so one wants to generalize this very nice story to other, well, other cases, and there are, well, several obvious, well, generalizations that one can come up with, and one is higher dimensions, and that was the theme of the previous talk. And so brain bricks are, yeah, well, 4-dimensional generalization of diamond models, and but that's not something I'm going to discuss today. So there are, well, 2 other obvious, well, directions for generalizations. One is to, well, non-toric, well, Calabi-Yau threefolds, and the last one is to think about non-commutative local toric and local Calabi-Yau threefolds. If it's non-commutative, then it's of course not toric. Well, maybe one can make sense of, well, non-commutative toric varieties, but that's we are not going to try that. So, well, so not in that sense, non-commutative is more general than non-toric. But so, and so before, well, working in dimension 3, let's, well, think about the 2-dimensional case, which is kind of a toy model, well, for the 3-dimensional case. So yeah, in dimension 2, well, we have, well, so AD classification that, well, everyone knows, and so the toric cases are exactly type A cases, and type 2 case is, well, you can, well, it's in some sense it's a quotient by, well, of type A case by a Z2 symmetry. Well, and you will see what I mean in the next slide. But so what is a diamond model in dimension 2? So it's a division of S1 into intervals. So in dimension 3, so a diamond model was a division of real 2 torus into, well, polygons. And in dimension 1, it's, well, much simpler. And instead of 2 torus, you have just S1, and you divide it into intervals. And in the, well, in diamond model case, well, nodes had colors, but in the, well, 2-dimensional case, these nodes does not have colors, and the dual, so the quiver is dual. So it's something like this. So this is the dual quiver, and arrows just goes like this. In both directions. So this is the Mackay quiver for, well, AN singularities, n is a number of, well, so for instance, this is 1, 2, 3, 4, 5, 6, 7. I think this is the A6 quiver. So yeah, well, AN is C2 mod, well, Z mod n plus 1 Z. So this is the correspondence. So and we think about the symmetry. So and the toric diagram is just an interval. So instead of a polygon, we have just had interval. So in the A6 case, well, we have something maybe it was not very good to draw the A6 quiver, or maybe maybe I should say, so this is affine A6 quiver. And we think of, well, and a diamond model. So we, well, in the A6 case, well, so we don't have, well, GL1 symmetry. Well, maybe I should explain the simplest case. So in the A1 case, so the simplest example is A1. And then, well, so this is a toric diagram. So just this interval is a toric diagram. And for instance, well, even simpler case is this, well, A0, which is just C2, and this corresponds to 0, 1. And this A0 case, or any other, well, AN for even n case, we don't. So this toric diagram doesn't have symmetry, but for the odd, well, AN case, well, we have symmetry of reflection. So this GLN, where n is just, well, one-dimensional lattice, has, well, a symmetry. And so we think about, well, taking quotient by that symmetry. So that symmetry will, well, flip, well, so acts on this, well, two-dimensional brain tiling, like this by flipping, well, and then if you take quotient, then you will obtain this kind. So this is the A5 case, and so well, these, well, vertex 1 and vertex 5 will be collapsed to vertex 1, and vertex 2 and vertex 4 will, well, be collapsed to vertex 3, whereas, well, these vertices 0 and 3 are fixed by this flipping. So, and then it will be split into 2 when you take orbifold. Well, that's how it works. And maybe I should explain more about why this kind of thing happens. But so basically, well, so the action on these vertices are free. So if you take quotient, then it will be just, well, collapsed. So the free orbit corresponds to, will be contracted to one vertex, whereas, well, this is the fixed point. So it will have, well, these correspond to non-trivial characters of the stabilizer. So if you have stabilizers, then, well, you get more vertices on the quotient. So anyway, so these two quivers shows how a quiver, well, for A5 singularity will be transformed into the quiver for D5 singularity by taking orbifolds. And so this is how things work in dimension 2. And in dimension 3, it's, well, much more. So in general, well, so we have much more varieties of singularities in dimension 3. So instead of just one, well, sequence of, well, singularities AN for, well, natural number n, we have, well, singularities classified by, well, convex, lattice polygons. And we ask when, lattice polygon have a symmetry by, GL to Z. And there are various interesting examples, like hexagon, for example, or there are many. So wallpaper groups, and it is classified, and so one of the fun part for us is that for each wallpaper groups there's a diamond model having that symmetry. To be more precise, wallpaper groups are subgroups of the group of Euclidean motions, and in that, and there are different wallpaper groups which essentially gives the same symmetry of the diamond model. But anyway, so for more figures you can take a look at this picture. Maybe I should have copied some of the figures to this slide, but anyway, I'm sure anyone interested in have already seeing the paper. I mean, during my talk you can do whatever you like, so it's much easier to read other papers while also listening to the talk. And so I decided not to copy something from that paper. But anyway, so and this theorem is the main result of this paper. So, and it basically says that so the most non-trivial part of this theorem is to find a consistent diamond model. So this consistency is some algebraic condition which can be stated combinatorially, but so it's a condition which ensures the Calabi-Yau free property of the path algebra. So you can draw arbitrary diamond model on a two torus, but often the path algebra of the resulting quiver with relations with potential does not have sufficiently nice property to describe the derived category of the toric variety. So this consistency is some condition which ensures, actually I think it's equivalent to the Calabi-Yau free property in the sense of Ginsburg of the path algebra. And so it's given any symmetric toric diagram delta, it's more or less easy to find a diamond model which have the symmetry of the toric diagram, but it's non-trivial to obtain a diamond model which is consistent in this sense. So and that's what this theorem is mostly about, and this will allow a nice description of toric this quotient. So this quotient is something more general than toric Calabi-Yau threefolds. That's quotient of toric Calabi-Yau threefolds by symmetry of the toric variety, which is not torus equivalent. So this quotient is no longer a toric variety, but it's very close to toric variety. So it's really a three-dimensional generalization of type D singularity. So this is a slight generalization of the theory of diamond models. So we consider diamond model and the symmetry. And so to obtain a quiver, you have to take quotient of the quiver. And the exact procedure or algorithm is described in this paper. And one curiosity is whether one can find isoradial diamond model. So isoradial diamond model is isoradiality is an even stronger condition on a diamond model. And so it is strictly stronger than consistency. And as far as I know, well, it is not known whether one can find a symmetric or isoradial diamond model. So it could be a good project for, say, graduate student, I think. So this is my joint work with Akira and Alvaro, and I will now move on to other direction of generalization. So it's a generalization in a non-commutative direction. So recall that the Mackay quiver for local P2 had 3 vertices and 9 arrows. So maybe I can draw it here again. So it was something like this. And we had only 6 monomials in the potential in the toric case, but you can add more monomials and more general linear combination of monomials to the potential. And so if we restrict ourselves to simple cycles, so in general, the potential can be something of higher degree, like going around here 100 times, but it will break the homogeneity of potential. So we want to keep the homogeneity. So we only deal with simple cycles. And then there are 27 monomials which can be added to the potential. And so if we add general linear combination, so something which does not appear as nodes of diamond model, then it will deform local P2 to local non-commutative P2. So it's something like the total space of the canonical bundle of a non-commutative P2 in the sense of non-commutative algebraic geometries like Artin Shelter and Artin Tate Vandenberg. So because there are many ways to add monomials, so there are many possible potentials. So we think about moduli of potentials. So for the local P2 case, a potential is an element of this vector space. So this is a 27-dimensional vector space, so spanned by simple oriented cycles in the quiver. So and the choice of basis has no intrinsic meaning, so it's natural to take quotient by the action of this group. And so then there is so these general linear group have centers, and so only one of them act effectively, and so we have two-dimensional stabilizer. So generically we have two-dimensional stabilizers for this action. GM just means C star. If you are not familiar with this notation, so it's GM stands for multiplicative group, which is just C star over the complex numbers. And and the moduli space of potentials is taking this is something called GIT quotient, geometric invariant theory quotient. So this symbol, but the definition is, well, simple, and just take coordinate ring of well, this vector space and take invariant part. So yeah, we forget about this GM and then take, well, invariant subring under the action of SL, and then take proj. So taking proj is like taking quotient by this C star, and this, well, invariant ring is something very classical, and it's known for a long time to be, well, a polynomial ring generated in degree 6, 9, and 12. So by taking proj, we obtain this weighted projective plane of this weight. So maybe I can. This is well, yes, something like, well, so there are 27 monomials. And this part, invariant ring. Generated freely. Six, 9, and 12. So this is, well, what the moduli of potential is. So this is, well, in a sense, moduli of non-commutative, well, local P2. So it's, in particular, is two-dimensional. And then what about non-commutative P1 plus P1? So in this case, well, so this also has a, maybe I don't need to remind, but so this has, so the diamond model description of this guy is this one. And so we have, well, so 4 vector spaces, each two-dimensional. And so we think about, well, the possible, well, cycles of length 4. So simple cycles are just elements of this vector space. So it's, well, 16-dimensional. And then we take quotient by this group. And so GID quotient, so it's defined similarly to the local P2 case. And in this case, well, again, the invariant ring is a polynomial ring, and this time generated in degrees 2, 4, 4, and 6. So the moduli space of potentials is a 3-dimensional weighted projective space. And then, well, we move on to, well, something even more non-foreign. Well, but this case, well, is related. So in the cubic surface case, so a general cubic surface is, of course, not toric, but it has a toric degeneration. So it can be degenerated to, well, a Zemo-3Z quotient of P2. So it has, well, 3 A2 singularities. And so it's a weak del Peso surface of degree 3. And so this one is toric. So this, well, cubic surface is in some sense close to toric case. But anyway, so in this case, we will have quiver like this. And so, and then, well, the potential is a sum of, this is a quiver for cubic surface itself and not that for the canonical band. So we have to take, well, maybe, yeah, you can call it periodic quiver, but so I should draw something like, and I identify, this column and this column. So the left side and right side should be identified to form. So this is kind of a periodic quiver. So it's a Zemo-3Z quotient of the quiver for P2, local P2. And then, there are many. So how many cycles are there? So there are, so starting from, this vertex, and then there are, I think, 3 times 3 times 3, so 27, cycles. And similarly, starting from these, I think, how should I think about it? And so, yeah. I think from here, starting from each vertex, there are 9 simple cycles, I think, and there are 3 so that as a starting vertex, you can choose one of these 3 ones. Of course, you can start from here or here, but wherever you like. But in total, you will have 27 simple oriented cycles on this periodic quiver. And then, for each arrow, so there are 27 arrows. And so you have the choice of basis of the arrow, which means rescaling the arrow. So in this case, so this GM is just GL1. So you have 20-dimensional space of potentials and 27-dimensional group of rescaling the arrows. And because this action has 8-dimensional stabilizer, a quotient will be an 8-dimensional space. So as a quotient, you will have 8-dimensional moduli of non-commutative cubic surfaces or non-commutative local cubic surfaces. Whether you put local or not, that doesn't affect the moduli. And so a non-commutative surface determines uniquely the non-commutative local Calabi-Yau threefold. So non-commutative cubic surfaces have 8-dimensional moduli, and the moduli turns out to be an 8-dimensional toric variety, and it has configuration space of 6 points in general position on P2. So a commutative cubic surface is obtained from P2 by blowing up 6 points in general position. So this configuration space is the moduli space of commutative cubic surfaces. And so that moduli space is a subspace of this 8-dimensional moduli space of non-commutative cubic surfaces. and this story generalized to any Del-Pezzo surfaces. So, and the biggest one is a Del-Pezzo surface of degree 1, which is P2 blown up at 8 points. And so the cubic surface case is associated with this triple of number 333. And so that 8-point blow up will correspond to this triple of numbers 2, 3, 6. So it will be like you have 2, 3, 6. Let's see that, and then you have quiver like this. Maybe too many arrows, but and you make it periodic like this. So there are many simple cycles, and then there are many arrows. So and you do the same story, and then you will get moduli of non-commutative non-commutative Del-Pezzo surface of degree 1, or non-commutative 8-point blow up. So and in the case of 8-point blow up, it will be 10-dimensional, I think. So and this is my final remark. And so this moduli space has especially in the case of non-commutative P2 and non-commutative P1 cross P1 has this kind of interpretation. So this and I'm not familiar with quantum information theory at all. So this is more like a remark. And but probably so it's more like a curiosity than. So I'm not sure if it can have some deeper meaning. Maybe it does, maybe it doesn't. But so anyway, so this So for instance, in the case of non-commutative P, non-commutative P1 cross P1. Let me think about non-commutative P2 case. So in the P2 case, we have P1, P. So potential belongs to this vector space, and this can be thought of as a quantum mechanical system consisting of 3 subsystems of which have 3-dimensional Hilbert space. So it's a quantum system with finite degree of freedom. So the Hilbert space is just 3-dimensional for one subsystem, and it's union of these 3 systems. And so if the system have 2, the dimension of the Hilbert space is 2, then it is called a qubit system. And then if it's 3, then it's called Q3. And so then somehow then moduli space of non-commutative P2 is the same as the moduli space of 3 Q3 states. And so entanglement it means that some vector in this vector space is a very special class of elements are those which can be described as V1. So if you take an element of V1, V2, and V3 and just take tensor product, then it will be some vector in this vector space. But in general, it must be a linear combination, and no general element of this vector, this tensor product cannot be written as in this form. And if it can be written in this form, then it's called separable. And if it's not, then the state is called entangled. So that's what entanglement means. But anyway, so I think this is what I have prepared. So I stop here. Thank you.
Thank you very much for the very interesting talk. Are there any questions?